Welcome to Talk Tensors. Imagine taking 16 of the world's most distinguished artificial intelligence scientists, sitting them down in a room, and having them carefully select the absolute best, most educational data to train a new language model.
Right, just giving them all the time they need to read through documents and, pick out the absolute gold standard of human knowledge.
Exactly. And then you run the math, and you discover that their expert choices are mathematically proven to be entirely worthless.
I mean, worse than worthless, actually. Their intuition about what makes an AI smart is actively holding the model back.
Which is just, it's wild to think about. Today, we are bringing you a deep dive into a project that completely shatters that assumption. We're talking about DCLM.
Yeah, the DataComp for Language Models project. And if you are tracking the bleeding edge of machine learning right now, I mean, this is the earthquake.
It really is, because for you listening, the entire industry has historically operated on this very hardware-first mindset.
Oh, absolutely. The mentality was always brute force.
Right, like building a bigger engine.
Yeah.
You just bolt on more GPUs, crank up the parameter count, and pour the entire raw internet into the compute blender.
Yeah, when a model hallucinated or failed at reasoning, the default diagnostic response was rarely to meticulously audit the trillions of words it read. The response was almost universally just to increase the compute budget.
Throw more money at it, basically.
Exactly. We treated the data as a static, unmanageable ocean, and compute was really the only variable we could actually control.
But DCLM introduces a diagnostic framework that proves the exact opposite. We are looking at a standardized testbed for data curation built around an unprecedented, staggering pool of 240 trillion tokens extracted from the internet.
It is an incomprehensible amount of text.
It is. And the mission for you today, as we explore this, is to understand why the era of compute obsession is ending. We're going to see how a simple algorithmic filter from years ago beats out the most complex modern LLMs at curating data.
Which is still my favorite part of this whole paper.
Oh, totally. And we're going to explore why human judgment is fundamentally misaligned with machine comprehension. Plus, we will look at how optimizing this data allows a fraction of a compute budget to go toe-to-toe with industry titans like Llama 3 8B and Mistral.
Okay, let's unpack this. Before we talk about how to clean the data, we have to grasp the sheer physical scale of the raw material we are working with here.
Right. So the raw material is the foundation of this entire enterprise, specifically a data set they call it DCLM Plawlor.
And we need to set the boundaries of this sandbox for the listener, right?
Yeah, so to give you the boundaries, it is a massive snapshot of the web pulled from the Common Crawl, but they placed a very deliberate chronological boundary on it. They only included data crawled prior to the spring of 2023.
Which is an essential quarantine measure, because if you scrape the internet today, you aren't just reading human thoughts anymore.
Oh, definitely not. You're just scraping other AI outputs.
Right. You are reading the output of ChatGPT, Claude, and Gemini, syndicating endless streams of synthetic text into blogs and forums.
Yeah.
You would be feeding the AI its own exhaust.
Which leads to model collapse, but that's a whole different deep dive.
True. So pre-2023 gives us a baseline of mostly human-generated text. But let's contextualize 240 trillion tokens for you listening.
Yeah, when they compressed all of these raw HTML documents using gzip, the physical footprint was 340 terabytes.
340 terabytes of compressed text. I mean, to put 340 terabytes of pure unformatted text into perspective, a standard plain text novel is about 1 megabyte.
Right.
So we're talking about the equivalent of 340 million thick novels.
It is a volume of text that a human being couldn't read in 100,000 lifetimes.
But here is the massive engineering wall you hit immediately. How do you run a scientific experiment on an ocean that big?
You really can't. Not easily.
Right, because if I invent a new way to filter out spam, and I have to train a 7 billion parameter model on 3 trillion tokens just to see if my filter worked, that is millions of dollars in server rental for one single test?
Yeah, and the financial barrier is the sole reason data curation remained a dark art for so long. Academic researchers simply could not afford to run ablation studies at the 7 billion parameter scale.
Because if you changed the data mix and the model improved, you never really knew if the new data was the magic bullet, right?
Exactly. Or if it was just a statistical artifact of that specific training run. The DCLM framework solves this by freezing the training recipe.
Freezing the architecture, the learning rate, the sequence length, all of it.
Yes, all the variables are locked. And then they introduce a multi-scale testing environment. This leads us to the discovery of what we can call the scaling law of curation.
This was the first major revelation for me. The idea that we can predict the behavior of a multi-million-dollar training run by looking at a miniature version of it.
It is incredibly elegant.
It's like you don't need to bake the 6-tier wedding cake to find out if the batter is spoiled. You could just bake a cupcake.
I love that analogy. And the cupcake in this scenario is a tiny model of just 412 million parameters.
Which is tiny by today's standards.
Oh, minuscule. But what the researchers mathematically proved is that performance at this tiny scale, when trained on just 8.2 billion tokens, correlates almost perfectly with performance at the massive 7 billion parameter scale.
That's insane.
We are talking about a Pearson correlation coefficient between 0.83 and 0.98.
Okay, let's break down that Pearson coefficient for a second, because that number is the key to the whole kingdom.
Yeah, we should define that.
A Pearson correlation of 1.0 means a perfectly straight line on a graph, right? Every time the small model gets smarter, the big model gets smarter by the exact same proportional amount.
Exactly. So hitting 0.98 means the predictive power is virtually absolute.
Which is huge. If a specific data filter boosts the 400 million parameter model, you can take it to the bank that it will boost the 7 billion parameter model.
And the architecture of this predictive test relies heavily on the chinchilla multiplier. The chinchilla scaling laws dictate the optimal ratio of compute to data.
Right, to maximize the intelligence of a model for a given compute budget, you need roughly 20 tokens of training data for every single parameter in the neural network.
And the researchers locked this 1x compute allocation in across all their scales.
So a 400 million parameter model gets about 8 billion tokens of data to read. It maintains that perfect batter to heat ratio.
Yeah, keeping the recipe identical, just shrinking the pan.
And the implication of this for you, the listener, is the total democratization of AI research. You no longer need a supercomputer cluster owned by $1 trillion tech giant to discover the next breakthrough in artificial intelligence.
No, you really don't. A university student with a modest standard GPU rack can download this 400M scale testing pool.
They can invent a novel filtering algorithm, run the training in about 26 GPU hours, and mathematically prove that their discovery will scale to the frontier models. It drops the barrier to entry down to the floor.
It's a total game changer for open source. But having the sandbox is only step one. Let's look at the actual mechanics of preparing this data.
Because extracting text from the internet is an absolute nightmare. The web is not a clean, continuous scroll of prose.
No, it's a chaotic mess of document object model trees. Navigation bars, pop-up ads, copyright footers, tracking scripts.
Right, and the standard operating procedure for the industry, the method used to build massive foundational data sets like C4 or Red Pajama, was simply to use the pre-extracted WYETI files.
Yeah, Common Crawl provides these files as a convenience. They run a basic script to strip away the HTML tags and leave you with just the text. It is incredibly convenient.
But convenience is the enemy of precision here. If we rely on those basic WYETI files, we are pulling in massive amounts of structural noise.
Tons of it.
Every single time a model reads a news article, it is also reading, home, about us, contact, terms of service, privacy policy.
Over and over again, millions of times.
Let's think about the psychological impact of that on a neural network's attention mechanism. The attention heads are desperately trying to map the fundamental underlying logic of human language.
They are trying to figure out how a subject relates to a verb, how a premise leads to a conclusion.
Exactly. So if you force that attention mechanism to process the phrase, click here to accept cookies 10 million times, it has to dedicate actual physical neural capacity, precious parameters, to modeling a completely useless syntactic pattern.
Which is exactly why the DCLM team abandoned the convenient wet files. They tested those against far stricter, more computationally intensive text extractors, specifically tools called Raciliparse and Trifilitura.
Okay, what makes those tools better than just stripping out the HTML tags?
Well, they don't just blindly strip the tags. They analyze the DOM structure of the web page to identify the main content node. They effectively ignore the sidebars, the headers, and the footers.
Wow. And the resulting leap in intelligence was massive. Just changing the extraction tool improved the downstream model's performance on core tasks by at least 2.5 percentage points.
Which is huge. In the context of machine learning benchmarks, a 2.5-point jump is a chasm.
Yeah, that is often the delta between an entire generation of models. We made the model significantly smarter just by removing the distractions from its textbook.
But once you have the clean text, you immediately run into the duplication crisis. The internet is built on syndication and repetition.
Oh, man. Duplication is arguably the most insidious poison in a training data set. You have exact duplicates, the same press release published on 1,000 different corporate blogs.
But the real challenge is near duplicates. Imagine a breaking news wire story that gets picked up by 50 local news stations.
Right. They keep the core paragraphs identical, but they alter the headline and add one local sentence at the end.
Exactly. And if we don't catch those near duplicates, we destroy the model's ability to generalize.
It's like a student studying for a calculus exam.
Yeah.
If the textbook features a wide variety of different problems, the student learns the underlying rules of calculus.
Right. But if the textbook accidentally prints the exact same specific problem on every third page, the student just memorizes the answer to that one specific problem.
Yeah. During training, the AI will over-index on that repeated sequence, and its gradients will skew heavily toward memorization. So, how do we hunt down near duplicates across 240 trillion tokens? The math involved here is staggering.
It really is. The industry has historically debated between two massive engineering approaches for this min-hash and Bloom filters.
Let's start with min-hash.
So min-hash is a locality-sensitive hashing technique. It is designed specifically to solve the near-duplicate problem by calculating the Jacquard similarity between documents.
Let's define Jacquard similarity for the audience, because it's a brilliant piece of set theory. It basically measures the overlap between two sets, right?
Yes. You take the total number of shared words between two documents and you divide it by the total number of unique words across both documents combined.
So if document A and document B share 90% of their vocabulary, they have a high Jacquard similarity.
Precisely. To calculate that across an ocean of data, min-hash relies on hundreds of different hashing permutations to create a signature for every single document. You then compare those signatures.
That sounds computationally exhausting.
It is incredibly nuanced and highly effective at catching those syndicated news articles. However, computing hundreds of permutations for billions of documents and constantly moving that massive signature index across distributed memory is computationally excruciating. It is slow and it is expensive.
So what did the DCLM team use to bypass that bottleneck?
They pivoted to a modified Bloom filter.
Okay.
A Bloom filter is an entirely different beast. It is a probabilistic data structure. Instead of creating complex signatures for whole documents, it uses a massive array of bits, just zeros and ones.
Okay, I want to visualize this because the mechanics are fascinating. The researchers use what they call a 100-way sharded Bloom filter, right?
Yes, and instead of looking at full documents, they looked at 13 token sequences, or n-grams.
You have a giant digital array. Every time the system reads a sequence of 13 words, let's say, the quick brown fox jumps over the lazy dog in the dense forest. It runs that sequence through a mathematical function that spits out a specific location in the array.
Right, and it goes to that location and flips the 0 to a 1.
Then, when it reads a new document, it checks the 13-word sequences. If the mathematical function points to an array location that is already a 1, the filter flags it and says, wait, we've seen this exact phrase before.
Yes.
This is a duplicate.
Exactly. The beauty of a Bloom filter is its memory efficiency. It does not store the words themselves, it only stores the flipped bits.
Which saves a massive amount of memory.
Exactly. And because of the probabilistic math, a Bloom filter will never give you a false negative. If it says a sequence is new, it is definitely new. However, it can occasionally produce a false positive.
Meaning, two completely different 13-word sequences might mathematically hash to the exact same array location.
Yes. But the team mitigated that by making the filter massive 100-way sharded, which dilutes the probability of those collisions.
And they found that 13 tokens is the magic number. I mean, if you check for 5-word matches, you end up throwing away common idioms like at the end of the day, right?
Right. And if you check for 50-word matches, the syndication variations slip through. 13 tokens hits the sweet spot.
And the result of this engineering pragmatism, the Bloom filter scales effortlessly to 10+ terabyte data sets and produces downstream models that perform virtually identically to the models cleaned by the grueling min-hack process.
It's a total triumph of efficiency over theoretical perfection.
So now we arrive at the frontier. We have extracted the text perfectly. We have mathematically purged the duplicates. We are staring at a massive, clean, unique pile of internet text.
But clean and unique does not equal educational.
Nope. We have to filter out the conspiracy theories, the unhinged blog rants, and the low-effort spam to find the actual gold. And this is where the entire narrative of artificial intelligence takes a massive, counterintuitive turn.
It really does. Because the logical assumption, the premise that almost every major lab has been operating under, is that to judge the quality of data for an AI, you should use an advanced AI as the judge.
It seems perfectly rational. If you want to know what a neural network needs to learn, ask a fully trained, highly capable neural network to evaluate the material. This gave rise to methods like Ask-LM, right?
Yeah. You take a powerful instruction-tuned model, you feed it a raw internet page, and you prompt it. On a scale of 1 to 10, how helpful and educational is this text?
And there were other highly complex algorithmic filters as well.
Oh, absolutely. Semantic deduplication, which tries to map the meaning of texts in latent space. Or perplexity filtering, where you use a baseline model to read the text. If the baseline model finds the text highly unpredictable or confusing, you throw the text away.
They even tested PageRank, assuming that web pages heavily linked to by other sites must contain higher quality information.
It's the assumption of complexity. We're building complex systems, so we assume we need complex gatekeepers.
But when the DCLM team actually ran the multi-scale tests, Ask-LM failed. Perplexity filtering failed. PageRank underperformed. None of them yielded the smartest downstream model.
Yeah, the undisputed champion for finding the absolute best training data was a staggeringly simple, lightweight, algorithmic classifier from years ago called FastText.
Here's where it gets really interesting. FastText completely ignores the complex, multi-layered attention mechanisms of modern LLMs. It is a linear model that looks exclusively at unigrams and bagrams.
That's it, just unigrams and biggrams.
Let's use an analogy here. If an LLM is a team of brilliant detectives analyzing the psychological motives, the timeline, and the complex relationships in a crime scene, FastText is just a simple scanner looking exclusively for fingerprints and footprints.
Right. Unigrams are single words, fingerprints. Bigrams are two-word pairings, footprints. FastText doesn't understand the narrative or the meaning of the document.
It just statistically analyzes the density of specific word pairs. And yet, this simple fingerprint scanner radically outperformed the brilliant detective. Why?
Because the secret wasn't in the complexity of the FastText architecture, it was in the reference data they used to train it. Normally, when researchers train a quality filter, they give it Wikipedia as the positive example of good data and random web spam as the negative example.
So the filter learns to look for the statistical fingerprints of formal, dry, encyclopedic language.
Right. But the DCLM researchers hypothesized something different. They trained their FastText classifier on a blend of two highly specific data sets. The first was OpenHermes 2.5.
Which is a heavily curated collection of instruction and response interactions.
Yes. And the second, and this is the absolute crux of the breakthrough, was a collection of high-scoring posts from the Reddit community, Explain Like I'm 5, or ELI5.
Explain Like I'm 5. For those who aren't familiar, this is a forum where a user asks a highly complex question like, how does a black hole warp time? Or why do immune systems attack transplanted organs? And an expert replies by breaking the concept down into the simplest, most fundamental pedagogical metaphors possible.
They completely avoid jargon. They use clear analogies. They build the explanation step by step.
Right. When the team deployed this ELI5 trained FastText model against the 240 trillion token sandbox, it aggressively hunted down and kept only the top 10% of documents that statistically sounded like an ELI5 explanation.
And when they trained a language model on that specific 10% slice of the internet, the downstream intelligence of the model skyrocketed. It provided a massive 3.5 percentage point lift over models trained on Wikipedia-filtered data.
I really want to pause and let that sink in. The model becomes measurably, objectively smarter when it learns quantum entanglement from a person on Reddit, using an analogy about tangled shoelaces, than it does when it reads a PhD-level physics textbook.
It is wild, but if we map that to human cognitive development, it actually makes perfect sense. You do not hand a kindergartner an oncology journal to teach them about the human body.
No, you give them a storybook that clearly maps the relationships between concepts. Dense, jargon-heavy text is incredibly difficult to extract generalized logic from because the concepts are buried under complex vocabulary.
ELI5 text is structured with a clear premise, a logical progression, and a definitive conclusion. The model isn't just absorbing facts, It is absorbing the fundamental architecture of reasoning.
Pedagogical data forces the explicit connection between cause and effect. And because FastText was looking at big ideograms, those two-word footprints, it was highly sensitive to the transitional phrases that indicate pedagogical structure.
Yeah, phrases like because of, leads to, imagine if. Simply put, the model thrives on that structured clarity.
Which brings us crashing into what we can call the human judgment paradox. If an ELI5 trained algorithm is so incredibly effective at finding this perfect data, why did the 16 AI scientists fail so miserably at the beginning of our deep dive?
What's fascinating here is how they tested this. To test the validity of human intuition, the researchers set up a rigorous manual annotation experiment. They took 500 documents from the web pool.
And they asked 16 expert AI researchers to read them and score them based on whether they thought the document would be high-quality training data for a language model.
Right. And the humans actually agreed with each other quite a bit. The inter-annotator agreement was solid. They established a clear human consensus on what constitutes good data.
So they found the documents with impeccable grammar, factual density, and professional tone.
Yes. But when the DCLM team took those human preference schools and mapped them against the actual empirical performance of the language models trained on those documents, the mathematical correlation was zero.
Zero. That is a chilling result. It means that the people building the minds of the future literally do not know what those minds need to consume to grow.
Human intuition had absolutely zero predictive power over machine learning efficacy. And here's the fascinating twist that ties it all back to Ask LLM. Remember how the advanced language model failed as a filter?
Yeah.
When they analyzed Ask LLM's choices, they found it had an 82% correlation with the human experts.
Oh, that is a devastating irony. In our obsession with alignment with training AI to mimic human preferences, speak in a human tone, and value what humans value, we inadvertently created an AI that perfectly inherited our blind spots.
Ask LLM chose the exact same useless data the human scientists chose because it has been conditioned to think like us.
It fundamentally highlights the divergence between human comprehension and statistical machine learning. When a human reads a document, we judge it based on narrative flow, aesthetic formatting, and factual truth.
We want text that is pleasant for a biological brain to parse, but an untrained, initialized language model does not have a biological brain.
Right. It is a vast matrix of randomized weights waiting to be organized. It does not care about narrative flow. It cares about rich vocabulary distribution. It needs specific token co-occurrences.
What a human expert reads and dismisses as dry, repetitive, or overly simplistic might actually contain the exact statistical density a neural network mathematically requires to carve a concept into its latent space.
The unigram and bigram signals that FastText detects are practically invisible to human conscious awareness, but they are the foundational nutrients for a neural network. We are building alien intelligence, and we keep trying to feed it human food.
We assume it wants a Michelin star meal of curated facts, but it actually just needs raw statistical protein.
That's a great way to put it. And if we accept that premise, it completely breaks the traditional pipeline of how models were assembled. For years, the gold standard in the industry has been the high-quality mix.
Yeah, where you take your cleaned web data, and to make sure the model is truly smart, you dilute the internet data with what we consider pristine sources. You mix in Wikipedia, published books, and ArcSiv research papers.
So what happened when the DCLM team took their mathematically perfect ELI5 filtered internet slice and mixed it with Wikipedia?
It actively harmed the model. The researchers took their top-tier dataset, which they named DCLM Baseline, and they mixed it with Wikipedia, books, and ArcSiv using the exact ratios made famous by open-source pioneers like Llama and Red Pajama.
And the result?
The result was a decrease in performance. Forcing the model to read those gold standard sources dropped its intelligence by 1.2 percentage points on the core evaluation metrics.
Wait, stop. I have to push back aggressively on this because it defies all conventional logic. You were telling me that an encyclopedia of human knowledge, peer-reviewed, grammatically flawless, factually verified, makes an artificial intelligence stupider than reading a curated pile of random Reddit threads, blogs, and internet forums.
It sounds crazy, I know.
How does the model learn actual facts if it isn't reading encyclopedias?
It comes back to the dilution of pedagogical density. Wikipedia is a phenomenal repository of facts, but it is written in a highly dense, referential, encyclopedic style. It states what is, but it rarely takes the time to gently explain why it is or how it connects to basic foundational concepts.
Right.
If your algorithmic filter is performant enough to find the absolute best educational explanations in the wild web, the natural linguistic diversity and the step-by-step reasoning found in that web data far outweighs the rigid structure of Wikipedia.
So by mixing in Wikipedia, the researchers were essentially watering down the concentration of the ELI5 data. They were replacing high-quality reasoning structures with dense factual structures, and the model's ability to generalize suffered as a result.
Yes, the model needs to learn how to think before it memorizes what to think, and Wikipedia teaches it what to think. That is a profound shift in data philosophy.
But whenever you see a model trained almost entirely on internet data performing this incredibly well on standardized reasoning tests, the skeptics' alarm bells have to start ringing deafeningly loud.
Oh, without a doubt.
We measure the intelligence of these models using standardized benchmarks, tests like MMLU for general knowledge or HelloSwag for common sense reasoning. These tests are published on the internet. People discuss the answers on forums. Are we absolutely sure the model isn't just regurgitating memorized answers? Did the AI just cheat by reading the answer key during its training?
The contamination question is the shadow hanging over every major AI release today. To prove that the intelligence of DCLM baseline was genuine and not memorized, the team implemented a fiercely aggressive decontamination protocol.
What did that look like?
They didn't just look for the names of the tests, they used 10-gram overlap checks. They took every question and answer from the major benchmarks, broke them down into sliding windows of 10 words, and scanned the entire 240 trillion token data set.
Wow.
Yeah, and if any web page contained an overlapping sequence of 10 words from an MMLU question or answer, they completely scrubbed that data from the training pool.
They actively hunted down the cheat sheet and ripped it out of the textbook. And after they removed the contaminated data, what happened to the test scores?
They trained a completely new model from scratch on the decontaminated dataset. And the performance remained exactly the same, and in some specific cases, slightly improved.
Seriously.
Yeah, on the HelloSwag benchmark, the score actually ticked up from 77.9 to 78.4 after the overlapping text was removed.
Which is the definitive proof we needed. The intelligence is real. The model didn't memorize the answers. It genuinely learned the underlying mechanics of logic, physics, and language from the ELI5 filtered data, and it applied that logic to solve test questions it had genuinely never seen before.
It is a huge validation of their filtering approach.
Okay, so all of these theoretical optimizations, the Donalware text extraction, the 100-way sharded Bloom filter, the fast text pedagogical curation, the refusal to dilute the data with Wikipedia, they are mathematically beautiful.
Yeah.
But theory doesn't put models on the global leaderboards. Let's look at the real-world performance. When they scaled this Goliath killer up to full size, what was the final recipe?
So they took all of these isolated discoveries and scaled them up to a 7 billion parameter model, training it on 2.6 trillion tokens of the DCLM baseline dataset.
Okay.
Now there is one caveat. Even the most perfectly filtered web data has natural blind spots. The wild internet is phenomenal for language and reasoning, but it lacks the extreme density of pure mathematics and executable code required to push a model to state-of-the-art status.
Sure, you don't find a lot of high-level Python scripts in an ELI5 thread.
Right. So to patch that vulnerability, they introduced a specific data diet shift during what is known as the cooldown training phase.
Let's explain cooldown for the audience. When you train a neural network, the learning rate, which dictates how drastically the model updates its internal weights, starts high, allowing the model to rapidly grasp broad concepts. But as training nears the end, you drop that learning rate significantly.
Because you are trying to settle the weights into their final, optimal, finely tuned state, that period of low learning rate at the very end of the run is the cooldown.
Exactly. And it is during that critical final stretch that they altered the data mix. They maintained 70% of their hyper-curated DCLM web data, but they injected 30% of a specialized mix containing StarCoder and ProofPile 2.
Which are incredibly high-quality data sets consisting of pure code and advanced mathematics.
They gave the model an intense, focused crash course in calculus and Python right before graduation day. And what was the final scoreboard against the rest of the industry?
The metrics are historic. On the MMLU 5-shot benchmark, which remains the most widely accepted standard for measuring broad general knowledge and reasoning, the DCLM 7B model achieved a score of 64%.
We need to contextualize that 64%.
Well, Before this paper, the state-of-the-art for language models trained on completely open data was a model called MAP-NEO. DCLM shattered MAP-NEO's score, beating it by a massive 6.6 percentage points.
And it achieved that dominance while using 40% less compute during training, right?
Yes. It's faster to train, significantly cheaper, and vastly smarter than the previous open-source champion.
That's incredible.
But the true shockwaves hit when you compare it to the absolute titans of the open-weight world models, backed by billions of dollars of corporate infrastructure. DCLM's performance is completely comparable to Mistral 7B v0.3, which scores around 63%.
And it is aggressively knocking on the door of Meta's Llama 3.8b model, which sits at 66%.
Right. But here's the statistic that changes the industry. DCLM achieved this performance parity while utilizing up to 6.6 times less compute than Llama 3.
6.6 times less compute. The sheer economics of that figure are staggering. We are talking about tens of millions of dollars in GPU time and megawatt hours of electricity. They match the performance of a trillion-dollar tech conglomerate's flagship foundational model using a fraction of the hardware budget.
Purely because they engineered a mathematically superior diet of internet text.
And they didn't rest on those pre-training laurels, did they?
No, they applied some sophisticated post-training polish. They utilized a technique called a grow linear sequence curriculum, gradually increasing the length of the documents the model reads at the end of training,
which successfully extended the model's context window from 2048 tokens out to 192 tokens.
They also instruction-tuned it, teaching it how to behave as an interactive assistant. When tested on the Alpakai Val 2.0 benchmark, it achieved a win rate of 16.6. That score outright defeats Google's Gemma Instruct model and approaches the highly refined Llama 3 Instruct.
So what does this all mean for you, the listener? We started this deep dive talking about the expectation of precision, the hardware X-ray machine. The ultimate takeaway here is that the era of brute forcing artificial intelligence with sheer supercomputing power is definitively ending.
It really is. Data quality compounds exponentially.
Compute is just the engine block. Data curation is the actual fuel. If you put hyper-refined, highly pedagogical rocket fuel into a smaller, cheaper engine, it will completely outrun a massive billion-dollar jet engine that is choking on the crude oil of unfiltered web spam.
And the algorithms required to refine that rocket fuel, like a simple fast text unigram scanner trained on Reddit explanations, are sitting right in front of us. They don't require an NSA-level data center to discover.
If we pull back and look at the trajectory of the entire field, DCLM represents a fundamental paradigm shift. It strongly suggests that the actual bottleneck to achieving artificial general intelligence is not how many H100 GPUs we can string together in a desert facility.
The true bottleneck is our profound lack of understanding regarding what information actually looks like mathematically to a neural network.
Okay, as always, we're going to wrap up with our novel notions segment. Just a quick disclaimer for our listeners. The ideas in this segment are purely for entertainment purposes and speculative exploration. We're taking the rigorous, peer-reviewed science we just discussed and projecting it into some wild but entirely plausible future scenarios.
I will take the first leap. Grounded in the mathematical proof that the performance of tiny 400 million parameter models perfectly maps to massive 7 billion parameter titans, I think we are looking at the imminent fracture of the monolithic LLM. I call this future the microcurator swarm intelligence.
I love the sound of that.
Yeah.
Walk us through the mechanics of the swarm.
Currently, the entire tech industry is driving towards centralization.
Yeah.
OpenAI, Google, Meta, they're all trying to build one single massive cloud-based trillion-parameter behemoth that knows everything about everything.
Right.
But DCLM proves that we can identify mathematically perfect data recipes using extremely cheap, tiny models. If that scaling law holds, the future of AI might be radically decentralized.
Okay, so what does that look like practically?
Imagine swarms of highly specialized 400 million parameter models running locally and natively on your smartphone or on a hospital's internal secure server.
Like thousands of little hyper-intelligent scout ships instead of one massive Death Star.
Precisely. You have one microcurator running on your phone that is specifically trained to hunt for and curate your personal legal and financial jargon. Another is deployed in a clinic, curating local medical logs.
Because we now possess the fast text ELI5 blueprint to extract perfect pedagogical signal from total noise without requiring heavy compute.
Exactly. These tiny models can endlessly curate hyper-specific niches of local data. They learn incredibly efficiently on localized hardware, and then they communicate their optimized latent representations with each other via a decentralized peer-to-peer network.
Wow, so we achieve localized, highly specialized, highly secure intelligence without ever sending a single byte of our personal data to a central cloud server. It would completely upend the data harvesting business models of the current tech monopolies.
It is the ultimate democratization of not just the open source models, but the data refinement process itself. You are running the oil refinery right on your phone.
That is a brilliant projection. Okay, here is my novel notion, and it builds on the sheer shock of the fast text ELI5 revelation. I call this the synthetic pedagogue Ouroboros.
Okay, lay it on me.
We learned today that neural networks do not want human narrative. They do not want our encyclopedias. They want perfectly structured, mathematically dense, pedagogical text. And we also learned that human experts are fundamentally incapable of writing or identifying this text reliably.
The human judgment paradox. We are the wrong species to write the textbook.
Exactly. So in the near future, we stop scraping the raw internet entirely. We abandon the common crawl. Instead, we take our current frontier models and we assign them one single monumental task: continuously rewrite the entire sum of human knowledge into mathematically perfect, pedagogical ELI5 formats.
Oh, wow.
They take all of physics, all of history, all of computer science, and they strip out the poetry, the narrative flow, the tangents, and the human quirks. They rewrite reality into a hyper-dense synthetic curriculum optimized exclusively for big-room token co-occurrence.
You are proposing a closed-loop feedback system.
And Ouroboros, the snake eating its own tail. Over the next 10 generations of artificial intelligence, new models are trained purely on these hyper-distillations. They never read a naturally written human sentence, they never read a blog post or a novel. They only consume the ultimate, statistically perfect synthetic educational feed.
We could reach artificial general intelligence drastically faster because the data efficiency would be absolute.
But it comes with a bizarre, almost philosophical side effect. The AI will have arrived at superintelligence without ever having experienced actual messy human culture. It will only understand humanity through a synthesized, pre-digested abstraction of our knowledge.
Which forces us to confront a highly unsettling question. If an AGI is trained entirely on a synthetic distillation optimized purely for mathematical machine learning, does its internal representation of reality begin to diverge fundamentally from ours?
Right. It would understand the physics of a tear, but would it understand the human context of crying if it never read the poetry describing it?
That's deep.
Which brings us to our final thought for you to ponder today. Think back to that medical X-ray analogy we talked about at the very beginning of the deep dive. We like to comfort ourselves with the belief that we are building an X-ray machine, a tool that looks at the world exactly as we do, just deeper and faster.
But if 16 of the world's top AI scientists cannot accurately identify the text that makes an artificial intelligence smart, what does that say about the fundamental, unbridgeable gap between human comprehension and machine learning?
Are we really building tools that think like us? Or are we painstakingly engineering alien minds that just happen to know how to mimic our language? Thank you for joining this deep dive on Talk Tensors. Remember, in a world obsessed with scale and hardware, keep questioning the data. We'll see you next time.